Good afternoon, classmates and teacher. We are the last team to present. We are made of Alan Eduardo Acosta, Brian Sochigua, Eduardo José Setién, Héctor Carmona, Iván Cabrera, Leonardo Cruz, Renata Camacho, and Vanessa Alcántara. In this presentation, we will talk a little about who Christian Otto Mohr was and his biography, differential cube, how to interpret formulas to build more circle, how it's graphed, its properties, how to build the Mohr circle in Excel, example of analytical form, and uses and applications.
The biography of Christian Otto Mohr, the one who developed the Mohr circle. He was born on October 8, 1835, in Holstein, in the German Confederation. He attended the Polytechnic School in Hanover, where he decided to study civil engineer. He developed an interest for mechanics and strength of materials, published theory papers about the strength of materials. He was really passionate about graphical tools, and he wanted to develop a method to represent in a more visual way the stress. Something similar was proposed by Carl Koman in 1882 when he developed the Mohr circle. He also developed the Williot-Mohr diagram, that we also know as the virtual force method. And what can we say about the Mohr circle? The Mohr circle is a two-dimensional graphical representation of Cauchy's law for a stress tensor. Mohr circle is often used in calculations relating to mechanical engineering or material strength. Also is used on geotechnical engineering and to test the strength of soils, and structural engineering to test the strength on structures. In 1874, Mohr formalized the idea of a statical indeterminate structure. As I was saying, he developed the Williot-Mohr diagram for truss displacements and the Maxwell-Mohr method for statically indeterminate structures. He retired in the 1900s and he passed on October 2, 1918, and 6 days before turning 84. Nowadays, Mohr circle is used on calculations related to mechanical engineering and material strength as one of the most simple ways to represent stress on two dimensions. Mohr also developed a failure criteria based on the Mohr circle. What can we say also about the Williot-Mohr diagram? Is that has a numerous of problems and that is what is not commonly used. That is only applicable on cantilever truss and in symmetrical truss.
Now, for a better understanding of the Mohr cycle, we will be using the differential cube, which this cube is used to represent the plane stress in the two dimensions, normal stress and shear stress. The normal stress, as we can observe in the image on the left, is from the x and y axis, while the shear stress is considered to be the z axis. This this differential cube. In this differential cube, it might be needed to rotate the object, and we will rotate the object to express the angle. We'll be searching for the stress element by using this differential cube, which is commonly represented in a 3D model, where you can observe that depending of where the forces are applied, it can be normal or shear. This stress element, as I said, can rotate and will rotate, and this rotation will not vary or change the stress of the element. It also represents the principal stresses, which are the maximum and minimum normal stress. Now, for a better understanding, we have the next example. In this representation, we have a tube where we want to obtain the main stresses in the section A. So, to obtain that, we will be using the differential cube, selecting the cross-section where the A is located, with the objective of having a better interpretation of the applied forces. We're gonna pick this section, draw a rectangle in this case, and we will draw the forces based on the x, y, z plane. After represented in 3D, we will have a better concept of how this will work. So we'll change it to a plane stress or a 2D dimensional draw. This draw will help us to obtain the forces, have a better understanding of how it's gonna work, where it's gonna move, or how it's gonna be deformed, and will help us to draw the Mohr circle.
Mohr's circle is traced on a stress plane. In said stress plane, the y-axis represents shear stress, while the x-axis represents normal stress. It is worth noting that positive shear stresses will be depicted below the zero mark on the y-axis. We first start by plotting the first 2 points in the graph. The coordinates to these points are the normal stresses in the x and y directions of the differential cube, followed by the shear stress with a positive and negative sign, respectively. Afterwards, we connect both dots with a straight line, which can be seen in a blue-green color in the image. As we can see, there is a point in the middle of the line, which would represent the average normal stress. If we trace a vertical line going from this point to the circumference, we would reach the point of maximum shear stress in the graph. Therefore, the maximum shear stress can be calculated geometrically, obtaining the radius of the circle. Other useful information can be seen in the points in the graph where the normal stress is at its maximum and minimum. These points, which are yellow in the image, could be obtained by adding and subtracting the radius of the circle from the average normal stress. Another piece of important information would be the angle theta p, formed by the blue-green line and the x-axis. This angle is exactly the angle at which the differential cube would be subjected to the principal stresses, multiplied by 2.
The job of the first formula is to obtain the angle of the triangle. It just uses the trigonometry property. Let me a second. Okay, it just uses this trigonometry property that tangent of theta is equal to opposite leg over adjacent leg. The next formula obtains the other side of the 90 degrees. It just subtract 90 minus 2 theta and obtain 2 gamma. And this is just resolve it. After that, we need to find the radius of the circle, but using the same triangle from before, we can see that the radius of the circle is actually the hypotenusa, so we just have to use the Pythagoras theorem. We just the opposite caret and the adjacent caret, then the square of them two, and then add them together, and make all of that the square root. The radius of the circle is actually the maximum shear stress, so we already have that. And now we need to find both of its extremes. And by that, we just need to know the center, who we already have, and add and subtract the radius of the circle.
Now, how to make the circle of Mohr? As number one, define the shear strength coordinate system for the normal and shear axis. Tensile normal strength components are plotted on the horizontal axis and are considered positive. Compressive normal strength components are also plotted on the horizontal axis are negative. Is this? Is this? Okay. Number two, define the torsional coordinate system. Shearing strengths are plotted above the normal strength axis. Is this this? Okay. Number three, plot the shear strength balance. Number four is plot the magnitude of the couple. Okay. Number five, obtain the center of the Mohr circle. Is obtained graphically by plotting the 2 points representing the 2 now states on a strength drawing and a straight line between the 2 points. Okay, the intersection on this straight line and the location of the center of the circle. Number 6 is draw the Mohr circle. And number 7 is stress analysis with the Mohr circles. Okay, thank you.
The properties of Mohr circle for plane stress are as follows. First, we have sigma A to the right of the circle. C is the center of the circle and also represents the average stress, and sigma B is to the left of the circle. These are located on the horizontal axis where the load is zero. In the image, we can see it as the axis that goes from negative sigma to positive sigma. Second, the principal planes are 180 degrees apart. The principal planes lie at an angle of 2 phi from the red line. We can observe it between that the line formed by coordinates at the point sigma and tau xy and the point sigma x and tau xy with the line of the horizontal axis. The maximum shear is at the top and the bottom of the circle, and the radius of the circle is the maximum shear. In the image, we have tau equal r.
So, to complement the presentation, we devised an Excel program where with only entering the values of the normal and shear stresses, we could obtain the main normal stresses and the maximum shear stress. The first step was to pour the formulas for the values relevant to the Mohr circle in a table and labeling the results accordingly. We use underscores to establish the axes and apostrophes to signify the main stresses. After obtaining the results, we needed a form to visualize them. So, first, we developed an array of angles going from 0 to 360 in interval of 10. This gave us the angle variables needed to form a circle. Then, using simple trigonometry and the results from the formulas, we obtained the x and y values. X values were given by the average normal stress plus the maximum shear stress times the cosine of the angle. Y values were given by the maximum shear stress times sine of the angle. These values made the Mohr circle in the graph. To graph the lines that connect the normal and shear stress, we only needed to select the values given to us by the problem and add them to the graph. This also worked for the maximum shear stresses.
Uses and applications. Mohr circle is often used in calculations relating to mechanical engineering for material strength, geotechnical engineering for strength of soils, and structural engineering for strength of built structures. In the same way, Mohr circles applies to situations in two-dimensional or three-dimensional stress states. As we can see in the image on the right, there are two common cases in which the study of stresses is necessary or easier to use with Mohr circle. In image 1, there is a bracket that was built with the wood grain in inclined direction. Subsequently, the shear forces and bending moment can be obtained in imaginary vertical cuts made as in the image on the right. The resistance of the wood in directions parallel and perpendicular to the fibers of the wood are usually known, which are sometimes different according to the direction, so the stresses found on the vertical face do not help us too much to know if the wood resists these stresses. If it's then when we must rotate the forces required to the direction shown to be able to compare them with the resistance of the material making use of the Mohr circle. In image 2, we can see another of its applications in the study of soils in the creation of the slopes. Slopes are slopes that mark a difference between the thickness of the lower sector of a wall and the thickness of the upper sector. This allows the wall to withstand the pressure of the ground behind it. Therefore, the failure is usually produced by shear stresses in the ground, so we must know the maximum shear stresses along the entire slope, and these stresses will almost never be in the vertical or horizontal direction, aligned with the x and y axis. So this is where we must apply knowledge of the stress rotation to know the maximum shear stresses at all points in the circle of Mohr.
Now, for the exercise number 1, it's quite an easy exercise. We first need to know the normal average stress by adding both the stress in x and stress in y and divide them by 2. We now have that the average stress is minus 55 megapascals. Now we need to find the leg of the triangle, which is obtained by subtracting the average stress over the stress in x. We now have that it's minus 15. Now we can use the formula that we saw before and just substitute all its elements and find that the theta, the value of theta, is actually minus 34. We can then proceed to find gamma by subtracting 45 to the theta to 45 and find that gamma is 10.28. We now find the radius of the circle or the hypotenusa. And this is simple, and now we have the maximum shear stress. We find both of its main stresses by adding and subtracting the radius, as we see before. And now we just have to graph. We have the center, it's over here. So we know that the center of the circle is on the left, and the larger main stress is negative, so all the circle is on the left side of this diagram. We know that theta is minus 34, so 2 theta is around minus 70, and 2 gamma is the remaining section. The maximum shear stress, we also have it, which is here, sorry. So we can add it. And the differential cubes are also simple. We just have to, and the first cube, which is the one with the main stresses, have by angle theta. It's the normal theta, not the multiplied by 2. So it's normal theta. And then both of these stresses are the main ones, the minus 12 and the minus 92. And the other one is the maximum shear stress. Its angle is gamma. Here we have 10.28 degrees. And it have the maximum shear stress and the average normal stress.
For exercise 2, the problem gives us a force of 190 pounds on the y-axis and a radius of 3/4 of an inch. We need to find the maximum stresses. First, we find the momentums on the z and x-axis made by the negative force on the y-axis. Then we calculate the moments of inertia and the polar inertia. To obtain the shear stresses, we multiply the momentum of x times the radius divided by the polar inertia. And to obtain the normal stress, we multiply the momentum of the y-axis times the distance between the neutral axis to the point we are analyzing, divided by the moment of inertia. We now understand that the normal stress of the y-axis generates tension, as we see on the diagram, and that the shear stress in the axis is positive, as it is clockwise. Now, as we already understand the formulas, so all we need to do is enter these values on the Excel sheet, and we can obtain the main stresses and maximum momentums and maximum shear stress.